Hi, welcome to Beginning Engineers. Today I'm going to be talking about batteries. Portable power. What is a battery? A battery is a device that converts chemical energy into electrical energy. If you've ever broken open a battery, you might have noticed that chemicals came out. A battery itself is made up of voltaic cells. A voltaic cell derives energy from redox reactions. Redox stands for reduction, oxidation. A redox reaction is when an electron is transferred between two items. So one item loses an electron, that's oxidation, and the other item gains an electron, that's reduction. Generally, in a voltaic cell, these two items are metal. So think about it. You have an electron flowing between two items. One definition of electricity is the free flow of electrons. So that's the process that is creating the electricity. But what is the layout, the design of the battery? Well, the voltaic cells in the battery are comprised of two main sections called half cells. Each half cell has its own electrode, which is a device that is an electrical conductor, so electricity can flow through it. One half cell has a negative electrode, called an anode. One half cell has a positive electrode, called a cathode. A battery is made up of these half cells, connected in series, that means in a line. Negatively charged ions, called anions, will migrate to the anode, and positively charged ions, cations, flow to the cathode. Each half cell contains an electrolyte solution. An electrolyte solution is an electrically conductive solution, so something that is good for electricity to move through. And yes, it's like the electrolytes in energy drinks. The human body needs electricity to operate. It's good if we have electrolytes in us. Cations are reduced, electrons are added at the cathode, while metal atoms are oxidized, electrons are removed at the anode. So for me, it helps to think of it as a positive section and a negative section, and you have charged particles moving to and through each of the sections. I think of it in a cyclical way. Things are going around, and those charged particles are being harnessed for power in whatever the device is. When you recharge a battery, it applies electrical current to reverse those redox reactions. Again, the reduction oxidation is how you get the energy from a battery. Reverse those redox reactions, and you're putting energy back into the battery. So you have your anions, your cations, your electrolyte solution that either has a anode or a cathode in it. They're connected in series, redox reactions are happening, and charged particles are flowing. That's your battery. But there's an electromotive force associated with that, an EMF. This is measured in volts, which makes sense, right? You buy a battery, oftentimes you'll buy it based on the voltage. The electromotive force is the electrical action produced by something that is not an electrical source. So what kind of electric action can we get out of this chemical battery? The net EMF of the cell is the difference between the EMFs of its half cells. The electrical driving force, or delta V bat, across the terminals of a cell is known as the terminal voltage, the difference, and is in fact measured in volts. The EMF and delta V bat of different anode-cathode combinations actually have standard amounts. This really surprised me when I did research for this video. I would have assumed the voltage of a battery came from the design, or how many half cells were in the battery. And I guess in a way the design is involved, but it's more so the properties of the anode and cathode that determine your voltage, not the quantity of half cells. And that's very interesting. I'll let you look at that table for a minute before we move on. It all might seem very complex, especially if you're like me and you're not well versed with chemistry. But I think something important to remember is that batteries are not using magical chemicals or solutions. They are taking advantage of material properties, and modern ones just have some of the best materials and designs we currently have. Almost any liquid or moist object that has enough ions to be electrically conductive can serve as the electrolyte for a cell. As a novelty or science demonstration, it's possible to insert two electrodes made of different metals into a lemon, or potato, or something similar, and generate small amounts of electricity. And that quote's directly from Wikipedia. Maybe you've heard of the potato clock. You can buy kits for this as science experiments. So really, batteries are just like more advanced versions of potatoes with two different metals in them. Sounds crazy, but it's something we've refined over the years. So let's take a look at the history of batteries. Recent discoveries have suggested that Mesopotamians could have used batteries as far back as 250 BC. This is called the Baghdad battery. The term battery itself was actually coined by Benjamin Franklin when describing Leyden jars being like a battery of cannon. A Leyden jar is an antique electrical component which stores a high voltage electrical charge from an external source between electrical conductors on the inside and outside of a glass jar. And you can see I have a picture on the right there showing a Leyden jar. So you've got a conductor that's kind of floating into the Leyden jar, but touching the inside conductor, which is foil in this case. You have the glass jar that separates two pieces of foil, one on the inside, touching that rod, the chain, and one on the outside. You would charge a Leyden jar using an electrostatic generator, which essentially is an old-fashioned machine that generates a spark through friction. So imagine a giant old-school friction machine. But then, that charge would be held in this Leyden jar because of the two conductors. Essentially, this is an old-school capacitor or condenser, which is another word for capacitor. So Leyden jars proved that you can hold on to an electrical charge in an actual physical device and release it later. From there, we have Italian physicist Alessandro Volta, who built the first electrochemical battery, the voltaic pile, in 1800. It was a stack of copper and zinc plates separated by brine, a salted water or liquid, soaked into paper discs. And you can see that image on the right. So just imagine that is a bunch of copper and zinc plates with salted water paper discs between them. It could produce a steady current for a considerable length of time. So it's not like you're just opening a Leyden jar and getting a spark or charge out of it. This thing output electric current for more than just a second or two. However, these were not considered practical because the voltage could fluctuate. That was until John Frederick Daniell created the Daniell cell in 1836 that was widely used for electrical telegraph networks. The first rechargeable lead-acid battery was invented in 1859 by Gaston Plante. Sorry on the pronunciation. So that's the history of batteries, and hopefully you can tell that they started as a more simple concept, and they've been improving steadily over the years. So for our current batteries, how do we describe them? How are batteries rated? Well, batteries are rated in capacity, the amount of electrical charge the battery can deliver at a set rated voltage. Capacity is usually measured in ampere hours, amp hours, which is a current multiplied by time measurement. So capacity is generally rated at a 20-hour interval at approximate room temperature. A 100 milliamp hour battery is rated to deliver 5 milliamp hours for 20 hours at room temperature. This can of course vary. The more electrodes, anodes, cathodes, half cells, a battery has, the greater the capacity. Going in a little further, you can see this table of common battery sizes and their ratings. So you've got AA's. They can be rated at 2700 milliamp hours, 1100, 3000, 1700 to 2700, 600 to 1000, or 1500 milliamp hours, based on the materials that they are made out of. Their voltage is typically 1.5 volts, and their standard size is 14.5 millimeters in diameter and 50.5 millimeters in height. And these battery sizes are standard. You have AAA batteries, same voltage as AA, but a slightly smaller diameter and slightly smaller height. The capacities are relatively the same, although they don't look like they vary as much. You have D batteries. They can go much higher in their capacity, 12,000 milliamp hours, 8,000, much higher than AA or AAA, although the voltage is the same. Their diameter is much larger and their height is larger as well. 9-volt rectangular. This is a very common rectangular battery. You'll see their capacity actually appears to be less than AA and AAA for most types. The voltage is 9 volt though, hence the name, and the dimension is rectangular, so a height of 48.5 millimeters, a length of 26.5, and a width of 17.5. And finally, we have button, coin, watch cell varieties. These batteries are the tiny circular ones that look like coins. They're typically 9 to 30 millimeters in diameter and 1.6 to 10.8 millimeters in height. Typically, their milliamp hours are 25 to 600, and their voltage is around 3. So their capacity is less than AA or AAA or D for the most part. And, like the name suggests, you can often find these batteries in watches. So those were common battery sizes and ratings, but what about common battery types? The chemical composition. Well, you have nickel cadmium. These usually have a voltage of 1.2 volts. They're inexpensive. They hold on to their capacity very well, even with many uses. However, they are almost completely banned in Europe due to cadmium being an environmental hazard. You have lead acid batteries. These are typically 2.1 volts and are often found in automotive batteries. So if you open the hood of your car and you see that giant battery, that's probably a lead acid battery. You have nickel metal hydride batteries coming in at 1.2 volts, also inexpensive. Better than alkaline batteries for high drain devices. So a high drain device would be a device that is constantly using the battery. Our cell phones, other similar gadgets, as opposed to a low drain device like a TV remote. It's only using energy when you're clicking the buttons. You've got nickel zinc coming in at 1.6 volts, also good for high drain devices, and supposedly no toxic components, so that's a plus for the environment. Silver zinc batteries, 1.86 volts or 1.5 volts. Expensive because of the silver, but you get a very high energy density, better than lithium ion even. So when doing some research on these batteries, I saw that silver zinc batteries were pretty common for hearing aids. When you have something that you prefer being small, like a hearing aid, energy density really matters for a battery. So you wouldn't want to use a gigantic battery for a small hearing aid because that would make it awkward. And of course, lithium ion coming in at 3.6 volts. These are probably the most well-known batteries today. They have high energy density and a low rate of self-discharge, meaning if you charge up the battery, it can sit there for a while and still have the same level of charge. Something to keep in mind with all these battery chemistries is you'll notice most of them have two items, silver or zinc, nickel or cadmium. And that's because one of the materials is used in the anode and the other material is used in the cathode. Regardless of the battery type and capacity, the sad day comes when the battery dies. But why do batteries die? How do they die? Oxidation consumes some of the battery material used in the cathode, and this makes that electrode less efficient at its task. Think of an old cleaning rag that soaks up less water as it gets worn out. I think that is a good example, a good comparison. Ions can get stuck during the travel between electrodes, so between the anode and between the cathode, and the actual electrolyte that each electrode is in can decompose itself, making that pathway for those ions less efficient. And finally, what does the future of batteries look like? And what are some warnings we should take into consideration? Well, the next phase of batteries could be advanced solid-state batteries. A team of engineers led by 94-year-old John Goodenough, professor in the Cockrell School of Engineering at the University of Texas at Austin, and co-inventor of the lithium-ion battery, has developed the first all-solid-state battery cells that could lead to safer, faster charging, longer-lasting rechargeable batteries for handheld, mobile devices, electric cars, and stationary energy storage. John Goodenough won the Nobel Prize for Chemistry and helped invent lithium-ion batteries, which is why people are very hopeful that this recent breakthrough could lead to more advanced batteries. The next quote on this slide, I'm not even going to attempt to read, but it's from the abstract of the research paper that talked about this breakthrough. Just notice some of the keywords there. It talks about charged ions, glass electrolytes, cations, anions, differentials. You can tell that a lot of this phrasing are things we just reviewed. And yes, this is at the most advanced level, but the basics still apply. There is a warning as well though. This new discovery could be all for nothing, as the difficulty with breakthroughs like this are they occurred in a lab, and it has to be scalable. Somebody has to figure out how to mass produce this technology at great volumes and affordably. And if you're watching this video, maybe that will be you. Maybe in 10 to 20 years, these solid-state batteries will be commonplace and we'll have much better energy storage for our cars, our homes, and our handheld devices. Thank you so much for watching this video. I hope you understand that a battery is comprised of an anode, a cathode, electrolyte solutions, and the flow of charged ions between the electrodes that are either giving up or gaining an electron due to the reduction, oxidation, redox reactions happening. And hopefully you know a little bit more about battery types and capacities. If you like this video, feel free to subscribe. I try to do an engineering video about once a month. Have a great day.